Mr. McBrien. This is SCH4U, balancing redox reactions 2, half reactions. So the Ontario curriculum specifies that we need to be able to balance reactions not just using oxidation numbers, but also using a half reaction method, and we'll see how to do that today. The good news is the approaches are pretty much consistent. Okay, so the half reaction method then, it has some advantages over the oxidation number method. The main one is that we track the electrons as part of the process, and so this gives us the ability to visualize the electrons that are being transferred explicitly. Now, we still have to acknowledge that most of the time we're going to work in aqueous solution, and this means that water can play a role, and we have to balance the atoms associated with water as well. Okay, so the basic instructions, and of course we're going to go through those step by step. The basic instructions, first off, write the chemical formulas for the reactants and products, and sometimes assign oxidation numbers. We'll start with the most complicated case, ironically, and use the oxidation numbers to track the electrons. This time, though, we want to break the reactions up into oxidation and reduction. Then balance the atoms that are not oxygen and hydrogen. Balance oxygen and hydrogen the way we did last time, using water and protons. And then we're going to balance the charge by adding electrons. And we have to be careful there to make sure that the charge is correct, paying attention to any of the numbers in front of the ions. Then we need to equalize electron flow. Remember that every electron that is given up must be accepted. Finally, we add the two reactions together and cancel any duplicates. If we work in base, then we also have to get rid of the protons by adding hydroxide, just like we did last time. Okay, so let's go through an example. So let's assume that we're oxidizing iron with dichromate, like in this reaction shown here. So dichromate is reduced to chromium ion, and iron is oxidized from 2+ to 3+. Okay, so let's take the oxidation number approach just like we did last time. Oxygen with the -2, chromium getting +6 just like last time. Iron is trivial. It has an oxidation number of +2 because that's its charge. Same thing with chromium. And the other iron with +3 because its charge is +3. Okay, not too tough. Then we want to separate it into two equations. So we have the one involving chromium and the one involving iron. And then we balance the atoms that are not hydrogen and oxygen. Pretty easy in this case. We just need to add a 2 to the right-hand side of the chromium equation. Iron is already balanced in terms of atoms. Notice not in terms of charge. Okay, the next step we need to take is we need to balance the oxygens. So, the chromium, of course, has 7 oxygens, the dichromate. So we need to add 7 waters to the right-hand side to balance those oxygens. Notice this is very consistent with what we did last time we used dichromate. And the iron one, of course, doesn't have oxygen, so we don't need to worry about it. Then we balance hydrogen. It's easy to see that now that we've got all that water there, we have 14 hydrogen atoms that we need to balance. So we add 14 protons to the left-hand side. All right, so far so good. And iron still stays the same. Now, the next thing we have to do is balance the charge. So this is where we depart from the previous procedure. So balancing the charge, let's go up to the top. We can see we have 14 plus -2 is a +12 on the left-hand side, but we only have +6 on the right-hand side. So to balance that charge then, we have to add enough electrons to take that, to add the electrons to the left-hand side to take that down to a +6. So we're going to add 6 electrons and balance the charge. And in the iron case, it's much easier than that. We had +3 on the right-hand side. We need to add 1 electron to that side. Now, what should be obvious to you instantaneously is we have 6 electrons on the left-hand side and only 1 electron on the right-hand side. No great surprise. To balance the electrons then, we have to multiply by 6. So what does that mean? It means that 6 iron atoms are going to be oxidized for every dichromate ion. Okay, so now we have balanced half reactions in terms of charge and in terms of electrons. Now all we have to do is add them together. So we add the two equations together to get the overall equation, and we cancel any duplicates. And this, of course, is huge for a few seconds. We have 6 electrons on both sides, and those are easy to cancel. And when we're finished, we have a 6, a 14, a 1 here, so we don't have many common denominators that we're going to be able to do that. Water's only on one side, protons are only on one side. Since this is in acidic conditions, we're done. So this is our first balance using half reaction method. And in basic solution, it's entirely consistent. 1 to 7 is just like an acid, and then we add hydroxide to remove that from the equation. Okay, so let's try one. Why not? So now phosphorus is going to be our target with the chromate ion. And we can go ahead and assign our oxidation numbers. As usual, hydrogen's +1, oxygen -2. From the +1, we can get the -3 for phosphorus. Get our 6 for chromium. Over on this side, we have a -1 overall for the hydroxide ion. Remember, hydroxide has a -1 charge. We could also, if we weren't sure about that, we could get a -2 for oxygen and a +1 for hydrogen, add them together, and we still get -1. So -1 times 4 gives us -4, but there's a negative charge here. So overall, we want a -3 to be balanced by this chromium. So it goes to +3. And finally, with phosphorus in its elemental state, that by definition gets a 0. Okay, we've got our oxidation states. We can break up into our half reactions. And then we want to balance the atoms that are not hydrogen and oxygen. So in this case, we're already balanced. Oh, no, we're not. My mistake. We've got 4 phosphorus here, so we have to put a 4 in front here. Okay, we can leave our chromate ion alone. Now we need to balance the oxygen. 4 oxygens here, 4 oxygens here. That's already balanced. Next, we balance the hydrogen. So this half reaction has 12 hydrogens. We need to balance that with protons. This reaction has 4 hydrogens. We need to balance that with protons. Finally, we use electrons to balance the charge. So up top, we have 0 going to +12. So we're going to need to add 12 electrons there. And then we have +4 -2 is +2, going to -1. We're going to need 3 electrons there, right? Okay, so now our electrons are balanced. Next step, for every electron we lose, we have to gain. And so we have to balance those electrons. 12 electrons here, 3 electrons here, multiplied by 4. Okay, so with that multiplied by 4, we can add these together and cancel any duplications. Of course, we know that the electrons are going to be balanced, and so they need to be canceled out for the overall equation. We also see some protons we can cancel, so we can subtract 12 protons from here and leave only 4 protons here. There we go. All right. So now our basic equation is here, but, bit of a pun, we have basic conditions that we need to account for. There aren't going to be many protons kicking around in solutions, so we need to change this up to make it reflect the fact that we're working in base. So what we wind up doing then is we add hydroxide to eliminate those protons. So we add 4 hydroxides to react with all those protons. Anything we do to one side, we have to do to the other. And then finally, we get to 4 waters on this side, 4 hydroxide on this side. Now, you might be tempted to want to divide by 4 since there's so many scripts of 4 in front of everything. But notice that this phosphorus is in fact P4. It's a molecule. And so we can't divide by 4 because we wouldn't reflect that molecular state of phosphorus here. So in fact, we're actually done. And this is our final reaction. Okay. One thing we should acknowledge here is that often half reaction method is much easier, in fact, than the oxidation number method. Why? Because we don't always have to use those oxidation numbers in order to get our half reactions. If we have our standard reduction table like we discussed yesterday, we can match the components in the reaction if they're given in our table and identify oxidized and reduced components in that way. And that can save us a little bit of time. So then all we do is transcribe the half reactions in balance. Now let's take the example we had from last time with oxidation numbers. We had dichromate and iron, right? So with this dichromate and iron example that we had to generate the oxidation numbers for, we could have moved across to our standard reduction table. This is the one that you're given in class. And we could identify the half reactions that are associated with it. So here's dichromate here, and here's iron here. Now notice what they've given us. They've given us the electrons that are involved and the protons. So they've done a lot of our work for us in this case. So we can go ahead and use those. Now the only trick involved is that this is a table of reduction potentials. Both of these reactions are in fact reductions, so we have to recognize that one of these components is oxidized. Can you see which one? Yes, iron, its oxidation number is going up. Iron's being oxidized. So we have to reverse this reaction. So dichromate is generating 6 electrons. Iron is going to accept those electrons. So we reverse that reaction and then we can add them together in balance as we did previously. Hopefully that's clear. So that's the only trick to using the standard reaction table is you have to recognize which one of the reactions has to be reversed, which one's being oxidized instead of reduced. Okay, to sum up, balancing redox equations, it remains more complicated than with other reactions because of tracking electrons. The half-cell method splits the reactions up into oxidation and reduction, and this has the benefit of allowing us to track the electrons themselves. When we want to balance in this method, we have to track the charge, hydrogen, and oxygen, as well as the atoms associated with each of the components. And in basic solution, we have to remember to add a hydroxide to eliminate all the protons, then cancel the water before we report our overall reaction. And again, you should always be doing the quick check to make sure that all the atoms and all the charges balance once you've finished. And if you've done it successfully, they should. Okay, for homework, please do the balancing half reactions worksheet and read through the note. Thank you very much. Have a great night.